Welcome back. Now let's look at the subtraction rule. It's also called the inclusion exclusion for two sets. If a task can be done in either n1 ways or n2 ways, then the number of ways to do the task is n1 plus n2 minus number of ways to do the task that are common. In other words, cardinality of A1 union A2 is cardinality of A1 plus cardinality of A2 minus cardinality of A1 intersection A2. Here is an example. How many bit strings of length 8 either start with 1 bit or end with 2 bits of 0, 0? Okay. You want to start with either 1 or end with 0, 0. Let A be the set of bit strings of length 8 starting with 1. B be the set of bit strings of length 8 ending with 0, 0. So number of the cardinality of A, that is number of elements in A, is 2 to the power 7. Why 7? It's an 8 bit, 8 length bit string. But one of the last one, this first one starts with 1, so there is no choice for the first one. You have choices for the second slot onwards. So 2 to the 7th. What about number of bit strings of length 8 which end in 0, 0? They end in 0, 0, so there are 6 different places left. Each place can have a 0 or a 1, so 2 to the 6th power. Now what is this intersection? Intersection consists of those bit strings which start with 1 and end in 0, 0. Okay, so there are 5 places still left, so it's 2 to the 5th power. In other words, number of bit strings which start with 1 or end in 0, 0, you see, is number of A union B, which is 2 to the 7th plus 2 to the 6th minus 2 to the 5th. This is by the subtraction. Okay. So assuming my calculation is all correct, it's 160. Okay. Now, a computer company receives 450 applications from computer graduates for a job. Suppose that 240 of these applicants majored in computer science, 180 majored in business, 70 majored in both computer science and business. How many of these applicants majored neither in computer science nor in business? Well, let's draw a Venn diagram. This is the universal set. U represents the set of all applicants. C represents applicants majoring in computer science. B represents set of students majored in business. So the intersection are students who had double major, computer science and business. We know there are 70 students here. We know that there are 240 in computer science, 180 in business. All right. So what does that mean? Number of students in C or B is number of students in C plus number of students in B minus number of students in C intersection B. So don't forget, you want to subtract the intersection once. Okay. The reason is C consists of intersection, so does B. In other words, you are counting this twice. That's why you are removing one count of the intersection. So students who are majored in computer science or business come to 240 plus 180 minus 70. So that's 350. So that's students who are majored in computer science or business. Now students who have majored neither in computer science nor business, in other words, they shouldn't be in this region, they should be outside. That will be all of universe minus C union B. So that's in all 100. Okay. Next, let's go to division rule. There are n over d ways to do a task. If it can be done using a procedure that can be carried out in n ways, And for every way W, exactly D of the n ways correspond to way W. Okay. If the finite set A is the union of n pairwise disjoint subsets, each with D elements, then n is cardinality of A divided by D. Okay. This is a bit abstract. Let's look at an example. How many different ways are there to seat 5 people around a circular table, where 2 seatings are considered the same when each person has the same left neighbor and the same right neighbor? Okay, so I have a circular table. The chairs are numbered 1 through 5. Okay, arbitrarily, you choose one of the chairs to be 1, and then the rest of the chairs are numbered as shown in the drawing. Okay, 1, 2, 3, 4. Now for the first location, there are 5 people, so 5 choices are available. Once a person is seated here, there are 4 people available for chair 2, 3 for chair 3, 2 for chair 4, and 1 for chair 5. So that's 1 seating. But notice, whoever was seated here, if I moved him here and 2 here, 3 here, that is, I rotated the table 1 position over, that gives me the same seating. Moving it 1 more position over gives me the same seating. So there are 5 ways of getting the same seating. So in all 5 factorial ways of choices and 5 rotations. So 5 factorial divided by 5 is 4 factorial. That's 24 different seating arrangements are possible. All right. The last way of counting diagrams is using tree diagrams. A tree consists of a root, a number of branches, leaving the root, and possible additional branches. Tree diagrams are usually handy when we really need to visualize what we are doing. How many bit strings of length 6 do not have 2 consecutive ones? Here is a tree diagram. Well, here is the root. For the first location on the bit string, you have 2 options, 1 and 0. If the first location is 1, the following one cannot be 1 because we are not allowed consecutive ones. Following one has to be 0. If this is 0, then you are allowed both 1 and 0. But if this is 1, you are allowed only 0. So you see the branches. So each branching is for an additional slot. First slot could be 1 or 0. Second slot could be 0 if the first one is 1. Or 1 if the first one is 0, 0 if the first one is 0, and so on. So reading it off, you can see 1, 0, 1, 0, 1, 0 is a string, possible string. 1, 0, 1, 0, and there is no 1, 1. So 0, 1, that's a possible another string, and so on. You can keep counting like this. There should be 21 in all. And these are the possible branches. So remember, we don't have any branch. If you notice, there is no 1 followed by a 1. So a tree diagram is a handy way of visualizing your different options, different strings. Here is another example. Suppose you cast a die and follow it with a toss of a coin. What are the possible outcomes? Well, here, first I cast a die and then toss a coin. So I could get a 1 and then heads, or 1 and then tail. Or I could get a 2 and then a head, and so on. So here are the possibilities. Let's list them down. 1 followed by a head, 1 followed by a tail, 2 followed by a head, 2 followed by a tail, 3 followed by a head, 3 followed by a tail, 4 followed by a head, 4 followed by a tail, 5 followed by a head, 5 followed by a tail. So how many are these? These 6, by the way. 6 followed by a head, 6 followed by a tail. So you have 12 different branches in all. So 12 different outcomes possible. Okay. This completes lesson 16. We will continue lesson 17 in our next video. Until then,